The following work presents the development of a novel form of grammar-guided genetic programming called tree-based grammatical evolution with non-encoding nodes, TGE-NEN. Grammar-guided genetic programming, GGP, is a type of genetic programming where grammar is used to generate the solutions. For each type of GGP, the structure of the genotype of the individuals is different. For example, grammatical evolution, GE, uses a linear structure where the genotype is a linear list. A structured grammatical evolution, both the normal and dynamic versions, SGE and DSGE, uses multiple linear representations, one for each non-terminal symbol of the grammar. And context-free grammar genetic programming, CFGGP, uses a tree representation. Our proposal will also use a tree structure for the genotype, where each node contains three attributes: a non-terminal symbol from the grammar that determines the type of the node, a number that determines the production that the non-terminal symbol expands once decoded, and a set of children nodes. The set of children nodes will contain both encoding and non-encoding nodes. The encoding nodes represent the nodes that are used when decoding the solution, whereas the non-encoding nodes are those that are not used in the decoding process. Figure 1 illustrates a portion of a tree. The upper node is of type expression, and the number 1 selects the second production in the right-hand side of the row. This production yields one non-terminal expression. Given this, from the children nodes, the only encoding node will be the first node of type expression. This example is highlighted using a blue background. If during evolution the number associated with the parent node changes, for example from 1 to 0, the production generated would now be the first one, expression operator expression. The new production contains three non-terminal symbols, therefore the encoding nodes are now the first node of type expression, which is the same node as for the previous production, the node of type operator, and the second node of type expression. This configuration appears in red hatch. As observed from the example, the children nodes are reused by the productions if they generate the same type of nodes. This characteristic palliates the inherent bloating of this type of structure, and it might help in the evolutionary process, since good subtrees will be reused by the different productions. The set of children nodes is generated dynamically. This means that when first creating a solution, the tree structure will only generate the nodes it needs for that specific expression. So at this point, all the nodes in the structure will be encoding. If after the evolutionary process one node generates a production for which it does not have the needed children nodes, it will generate them dynamically. With this structure, evolution happens on two levels, encoding and non-encoding. For the evolutionary operators, we've implemented a crossover and a mutation operator. In terms of the crossover, the one implemented is a general subtree crossover performed over two subtrees whose root nodes are of the same type. The limitation added is that only encoding nodes can be chosen to perform crossover. As for the mutation operator, the basic integer flip mutation has been implemented. This mutation is performed over the numbers associated with the nodes that determine the next production to be chosen from the grammar. The values that the numbers can take are between 0 and the maximum number of productions of a specific non-terminal minus 1. The limitation added to the mutation is that only encoding nodes can mutate, and once the root of a subtree has mutated, the process stops for that subtree. This is due to the fact that once the root mutates, the generated subtree will also change. The algorithm has been tested for the 11-bit multiplexer benchmark in comparison with GE, the SGE, and CFGGP. Table 1 contains the experimental setup, where 30 runs are performed, each of 1,000 generations, with a population size of 200. Ellipticism has been set to 2%, and the initialization is random for the 4 algorithms. The mutation and crossover operators are the basic operators for each algorithm type, including the one we just described for TGE-NEN. Figure 2 shows the grammar used in the multiplexer problem. The results can be 1 or 0, therefore the fitness function used for the evolution will be the absolute error. A perfect solution will yield fitness 0. Figure 3 contains the evolution of the best solution of the 1,000 generation for each of the 30 runs. The solid line represents the average, and the error bounds the standard deviation of the best solution of each of those 30 runs. It can be observed that our proposal performs better or equal to the other GGGP alternatives regarding the final fitness values in training. TGE-NEN starts the evolutionary process very similar to CFGGP and is better than both TSGE and GE. In generation 150, TGE-NEN starts to give better average results, diverging from CFGGP, and the fitness difference keeps increasing until the end. From this preliminary results, we can conclude that the structure proposed aids during the evolutionary process, yielding better results than the other structures considered. In terms of future work, this structure must be tested further, as the non-encoding nodes add a lot of extra memory, and depending on the grammar structure, they will become a bloating issue. We shall also perform the study on other benchmarks and test other crossover and mutation operators.